Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline, you'll need somewhere to deploy it, so check out Linode. With private networking, shared block storage, node balancers, and a 40 gigabit network, all controlled by a brand new API, you'll get everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode to get a $20 credit and launch a new server in under a minute. And are you struggling to keep up with customer requests and letting errors slip into production? Want to try some of the innovative ideas in this podcast but don't have time? Data Kitchen's Data Ops software allows your team to quickly iterate and deploy pipelines of code, models, and datasets while improving quality. Unlike a patchwork of manual operations, Data Kitchen makes your team shine by providing an end-to-end data ops solution with minimal programming that uses the tools you love. Join the data ops movement today and sign up for the newsletter at datakitchen.io/DE. After that, learn more about why you should be doing data ops by listening to the head chef in the Data Kitchen at dataengineeringpodcast.com/datakitchen. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. Your host is Tobias Macy, and today I'm interviewing Sage Weil about Ceph, an open-source distributed file system that supports block storage, object storage, and a native file system interface. So, Sage, could you start by introducing yourself?
Sure. My name is Sage. I'm the Ceph project lead. I've been working on Ceph since the beginning, which is almost, 13 years now. The first line of code was written in 2004, so thereabouts. These days I work at Red Hat. I'm part of the Office of the CTO, but my primary focus is on the Ceph upstream project, setting the technical roadmap and trying to get as much time as I can to spend actually doing coding.
Yeah, it's difficult. Some days you end up having to just write a bunch of prose.
Lots of meetings, lots of video conferencing.
And do you remember how you first got involved in the area of data management and data storage?
I co-founded a web hosting company out of college in Los Angeles area, DreamHost. And so storing all the customer data was sort of one of the problems that we dealt with, but wasn't really my primary focus. But when I went to grad school at UC Santa Cruz, I joined a research group that was focused on storage and became involved in a project that was funded by the national labs, Los Alamos, Livermore, Sandia, basically focusing on building a petabyte scale distributed file system. And that's really where Ceph began.
And as I understand the history, you ended up using Ceph fairly extensively at DreamHost as well to serve as sort of the underlayment for a lot of the virtual machines that you ran.
Yeah, although it took us a long time to get there. So the project began as sort of a research project, and I think I underestimated the amount of work it would require to turn into something that you could actually use in production. So it was actually, even after leaving Santa Cruz and focusing just on developing the upstream project, it was years before it was actually used in production at DreamHost or anywhere else. But I guess it was 2011, 2012, thereabouts, we launched a S3 compatible object storage service called DreamObjects. And it was also around that time that Ceph really took off in the OpenStack space and was used by lots of people for block storage for virtual machines. And DreamHost was among many users in that space.
And beyond just being used for the sort of platform layer for virtualization and cloud hosting, what are some of the most common and widely used use cases for Ceph?
So Ceph provides object block and file as well as sort of a lower level native object store. So there's sort of like four main interfaces that people use to talk to the store system. The most common are definitely currently in the block storage space for virtual machines, where Ceph is used by the OpenStack community extensively, lots of other virtualization tools. Like there's a system called Proxmox that's really popular, especially in Europe. And then also on the object side for the Rados Gateway, which provides an S3 and Swift compatible object storage service, both for individual clusters, and you can federate multiple clusters together. So those are, I'd say, the bulk of the users are in those two spaces. In the last few years, as we've finally declared that the file system is sort of stable and production quality, the file system usage has also picked up significantly. but I think it's not quite as extensively used as block and object still.
There are a large number of different distributed file systems, most of them focusing on maybe one of those areas of being a block versus an object versus a file system layer, or being purpose built for a particular use case. So, how do you view Ceph in terms of the broader landscape of offerings for distributed file systems?
Well, a couple things. It was originally intended to be a distributed file system, and so the overall architecture was targeting high performance computing workloads on supercomputers with thousands and thousands of nodes, piling into the same file system, these big crazy workloads that, bazillion people creating files in the same directory, that sort of thing. That was really where it started. But the architecture that we came up with to support that use case was layered in the sense that we had an underlying object storage layer that came to be known as Rados, and then the file system functionality was really built on top of that. And I think it was sort of an accident of fate. It wasn't really what we intended. That sort of object layer was generically useful for all kinds of different storage. So it was a few years later that we added the block device that basically just stripes a virtual disk across objects. Initially, it was pretty simple. Now it's got all kinds of other features as well. And similarly, that we built an S3 compatible RESTful object storage gateway that also stores its data inside Rados. The system wasn't really intended to be all of those things initially. What really did motivate us though was sort of a relentless focus on scale. So the way that the Rados was architected, it was designed to try to eliminate any sort of single point of failure clearly, and also any sort of single point that would limit the overall scalability of the system. That and a view that we wanted to build a system out of components that were expected to fail, whether it's a hard disk or SSD or a network card or a host or an entire rack of servers. So the way that Rados is put together is very different from sort of the other distributed file system that was used at the time in HPC, which was Lustre, where you had sort of pairs of nodes and a sort of a traditional failover pair with dual connected device disk arrays and so on. It was really specialized hardware and sort of a traditional approach to doing HA. Ceph was very much of the view that when you're building a system that's really big, things are always going to fail. Sometimes they're going to fail in place. You're not even going to be able to replace them. And you really want to be able to build a system out of commodity components and have it still provide a high level of reliability.
So, in the fact that you were designing for high failure rates and commodity hardware, you were in a lot of ways anticipating the current trend towards what's being referred to as cloud native architecture, and also a lot of the work that's being done on some of the systems like Hadoop, where you're relying on these just off the shelf hardware or virtualization components to be able to build these massively scalable and reliable systems, rather than having to invest in very high cost purpose built hardware that doesn't necessarily allow you to scale as quickly and as easily in the cloud era.
That's exactly right. And I think it's interesting that my recollection, at least, of at the time what we were thinking, it really wasn't, we weren't thinking cloud at all. Like cloud wasn't even really a buzzword at that point. This is 2004. We were really thinking about supercomputers. And it's interesting because today the way that these systems are deployed, it's like a lab will buy a new supercomputer every like 4 or 5 years or whatever it is, and they deploy a bazillion racks, and it sits there and it doesn't change for the life cycle of that machine, which is going to be like 5 or 7 years, however long they keep it running, and then they tear it all down and like build a new one the next building over. But when we were designing it, we were very much thinking about the idea that these systems had to be dynamic. So we were sort of thinking beyond the way that the HPC systems were sort of run at the time, that you would deploy new hardware incrementally, you'd have a mix of different types of hardware, some stuff would fail, it'd be decommissioned, new stuff would be deployed, and so on. So we're imagining this sort of system that would live, have a much longer life cycle, that would live continuously. But I don't know. It's interesting because I don't remember thinking of that in terms of cloud, but that's very much the way that sort of real systems, how their life cycles look today.
Yeah, and particularly the fact that it was built with no single point of failure is what allows it to continue to be relevant, whereas some of the older systems, such as Gluster that you mentioned, are starting to fade from the common discourse because they aren't really able to keep up in this cloud era where you have new instances coming into and out of existence very rapidly and automated deployment capabilities. So having that scalability and the ability to delegate across multiple nodes in the cluster for that scaling really makes it able to keep up as new types of workloads are introduced.
Yeah, I mean, we definitely focus on the idea that a cluster is a very dynamic entity. You're always adding and removing nodes, and they can sort of be put anywhere, and anything can happen at any time. To be fair, Gluster does have a lot of these same features, but it is true that it's a lot more structured in the way that you add and remove nodes. So you have to be added in pairs and have to be aligned, and the way that it rebalances is a little bit less flexible. But I think that the sort of relentless focus on unreliable hardware, being able to cope with that, and sort of arbitrary changes to the cluster configuration are what makes the Ceph architecture very compelling in these environments.
And one of the most notorious issues in these types of distributed and scalable systems is network partitions and network failures, and the whole concept of the cap theorem and the limitations that that imposes on computing structure. So, what are some of the ways that you have worked around some of those failure modes and worked to mitigate the impact of network partitions and some of those other types of events that can happen in these large clusters?
So in Ceph, the way that we deal with partition is by relying on the monitors, which are sort of the gatekeepers and cat herders of the system. They run our implementation of Paxos. And so you always have to have a majority of the monitors online and available in your partition in order to make progress in the system. But as far as the way that the actual data is laid out on disk and how we replicate writes and so on, we faced a sort of a design decision whether we wanted to have sort of like a two-phase rollback type system, or you could, or how complex and how involved we wanted to make that, the protocol of actually applying a write to multiple replicas. And what we ended up doing is sort of walking this fine line where the system sort of, optimistically is assuming that all replicas are going to be able to apply the write, and it does so. And the way that we maintain global consistency in the system is by relying on a global view of who the replicas are and which ones are allowed to write at a particular point in time that is managed by the monitors themselves. So if you end up in a network partition on the side of the monitors that don't have enough of them available to form a quorum, then you aren't able to form a view of the system that allows you to write. And so that half of the cluster isn't able to make progress. And it means that we don't have to use a quote unquote heavyweight protocol like Paxos for every IO, but instead only use Paxos for forming that consistent view of who is allowed to write, and then can use a more efficient protocol to actually do it.
And so, in the event of a network partition, it sounds like you would go into a read-only mode where you're still able to access existing data, but the systems on the partitioned side just aren't able to create new data, so that you don't end up in an inconsistent state when that partition is resolved.
Right, although in reality you can't actually allow clients to read data either on the partition side because they might be reading stale data. And the level of consistency that Rados is trying to provide to clients is, I think the technical term is full serializability, although I'm not actually a database expert, so I might be wrong there. But for a user, for example, a block device or a file system, those applications are expecting perfect read after write consistency, and so you can't actually allow them to read from the partitioned stale side or whatever, because it might not be the most up-to-date version of that content.
And also, in the case of the POSIX compliant file system view, any read would also entail a write by modifying the A time or the M time of the file that is being interacted with.
If we aspire to do fully consistent A time, then yeah, that'd be correct. In reality, we just don't really do A time because it's so inefficient and so expensive. I think
Fair enough.
What Linux has done is the rel A time concept, where A time is updated if it's newer than the M time, so that you at least have this notion of whether the file has been accessed since it was last modified, which is in reality the only real semantic that actual user applications rely on. And to be fair, Ceph even doesn't actually implement that directly. We just are relying on the client kernels that are actually mounting the system to apply those A time updates when they're relevant.
And so, in terms of the implementation of Ceph, how is the software actually architected, and what sorts of evolution has it gone through over the period of time that you've been working with it?
Right. So the system is broken down into a set of, I think it's like four, five, six different daemons, depending on how far you go down the list. I already mentioned the monitors. There are usually like five of these in a cluster, maybe seven. If it's a small cluster, maybe you only have three. These are the nodes that are running Paxos and are managing sort of the critical cluster state about who's a member of the system, all the authentication metadata, and so on. What the current IP addresses of nodes are, whether they're up or down, that sort of thing. Those are managed by the monitors. And they're actually the only component in the system that has sort of a well-known advertised IP address. So when you quote unquote mount the system, whether if you mount the file system literally or whether you're accessing a block device or whatever, they're the first ones you contact to authenticate and then find out about all the other daemons and nodes in the system. And what their current state is. So those are the monitors. The sort of the next most important daemon is the OSD, the object storage daemon. And these are daemons that manage an individual local storage device, or possibly a pair of them. So usually there's one OSD per hard disk or per SSD. And so in a typical box with like, I don't know, 12 drives or something, you have 12 of these daemons running. And they're the ones who manage storing objects on that local device. And then they also talk to each other and to clients to service IO requests and to replicate writes or to migrate data between daemons. And sort of the driving concept with the way that Ceph and the Rados object layer is put together is that these are smart daemons. So most distributed systems and most storage systems end up with something similar to an OSD, but it's usually sort of a passive entity where it comes up and it sits there and waits for you to ask it to read and write data. And then something else external to them is reading data and writing it and moving things around, but they're just sort of sitting there as a passive entity, sort of like a hard disk. In contrast, the OSDs are more active in the sense that they talk to each other. They talk to the monitors to find out what the state of the system should be, where the data should be distributed, and then they sort of work in cooperation with other OSDs to make that so by migrating data around and ensuring that IOs are properly ordered with respect to data migration tasks and so on. So together the monitors and the OSDs provide sort of this pool, this low-level Rados pool of objects that everything else is built on. There's a relatively recent addition of what's called a manager daemon. That's sort of similar to the monitor, but it's stateless and it's more pluggable. So earlier on in the system, the monitor was also tasked with keeping track of stats about how much data is being stored and how it's being used. So we could implement things like DF. All of that workload has been moved onto the manager so that it isn't being like funneled through Paxos, which ended up being a performance issue and scaling bottleneck. And then the manager is also written in such a way that you can write Python plugins to implement various management style things. So, for example, there are new modules that will expose the Ceph health to or metrics to Prometheus for exporting stuff, or InfluxDB, or send health reports to Zabbix. There's a new module in the process that's scraping smart statistics and is going to run like a prediction model about disk failure. All those sorts of things are sort of like not critical to actually making sure the data is stored in the right place at the right time and isn't going to get lost, but are important sort of background management functions for the cluster that are much easier to write in Python and sort of open up this whole ecosystem of contributions and integrations. So that's a relatively recent addition to the system, and it's been pretty successful. We've seen like a half dozen user contributed modules already, adding all sorts of interesting new functionality. And then for the file system, there's another daemon called the metadata server that handles the file system namespace. So for the file system, clients talk directly to the OSDs to read and write IO to files, and then they talk to the metadata server to traverse the file system namespace to list directories. And there's a very complicated client-server protocol there for providing leases to the clients to let them know when they're allowed to write directly to files and when they're not, when they have to do all the locking and so on there, and manage all the client caches to make sure they're fully coherent. In the case of CephFS, we aim for fully coherent client caches so that two processes interacting through the file system will have the same result if they're running on the same host versus if they're running on different hosts talking through CephFS, which is a lot of work, but provides a lot of value for for applications. And then more recently, there are a couple other sort of extraneous things. Oh, there's the Rados Gateway, I guess I should mention. That's also a daemon that sits on top that's providing an S3 endpoint. So it's allowing you to store S3 style RESTful objects in Rados and exporting an API that implements a whole bunch of stuff in S3, everything from like quotas and ACLs and so on to doing multi-site federation of Ceph clusters to replicate data across sites and all that kind of stuff.
Yeah, it's definitely a very broad project that seems to encompass a lot of different use cases, and in many ways appears as though you could use it as part of a multi-cloud strategy to abstract out some of the specific services from different cloud providers and manage them on your own if that's something that you are particularly concerned with.
Yeah, I mean the scope of Ceph has definitely grown over time. Originally it was just a file system, then it was also block and S3 object store, and today it has all kinds of multi-site federation capabilities. And that's very much, I think, part of our roadmap too. As we sort of look at the IT landscape, it's clear that organizations don't just have their like one data center where they put all their stuff, but they have multiple data centers at multiple sites, at branch offices, and so on. And then they're also leveraging the public cloud. And so tying all that together and managing their data across them, this whole like new data services term, I guess, which applies to the mobility and the policy and insights and everything into what data you're storing and where it is and where it should be stored, and automating the management is very much where we're going. I think that's most relevant in the object storage space, because I think a lot of these new generation of cloud native applications are and should be targeting object storage because it provides sort of the right fit as far as the semantics of object storage to what the mobility requirements are going to be and scalability requirements. So it's much easier to make an object store replicate across multiple sites in an asynchronous fashion and do that in a consistent fashion than it is doing that at like a block device or a file system or whatever. It's much more challenging to make sure that you don't introduce conflicts into the system. So there's a lot of work going into the RGW roadmap to make that all a reality. We already have this multi-site federation capability where you can set up multiple Ceph clusters all over the place and tie them all together into a sort of a single unified namespace of buckets and users. This is sort of analogous to what you get with the S3 from AWS, where you have a bucket name and the system sort of knows via DNS and all its internal metadata where to send you what region that bucket is actually stored in. RGW provides you sort of a similar capability, in addition to letting you do disaster recovery, sort of replication, and even active-active replication, where you can write to either side of a replicated set and it'll send the data in the other direction. But we're looking to extend this to a sort of a much broader set of capabilities as well, where we can like automatically manage the migration of buckets between sites, apply policy to where objects go, push individual objects to sort of tier them out to external public cloud storage and possibly encrypt them, and the whole sort of gamut there.
Yeah, and as we get more powerful abstractions for enabling some of these multi-cloud capabilities, most notably things like Kubernetes and other container orchestrators that provide a unified API for being able to run regardless of what the underlying platform looks like, being able to also extend that into the file system and object storage capabilities makes the whole what used to be a fantasy of multi-cloud capability closer to being a reality.
Yeah, Kubernetes is a really big piece of it. It's sort of struck the right balance and note and allowing people to automate and abstract the way that applications are deployed across multiple clouds, or at least across a single cloud. I think the whole multi-cloud operator is sort of the evolving next step, but lots of people are certainly working on that. But sort of the Achilles heel of that, or the elephant in the room, or whatever metaphor you choose, is really that there's all this state associated with your application, all this data that also needs to be portable and accessible from multiple locations. And if you're, it's one thing to sort of redeploy your application on another cloud, but it's another to like migrate an existing application with a whole bunch of state, all the databases and objects and so on, actually pick that up and move it somewhere else and do that in a way that keeps that application running and online the entire time. And so I think today we have most of the sort of underlying building blocks in Ceph to allow that to be possible, with the object storage, replication, federation capabilities. And even in the block storage layer, we have an asynchronous replication capability where you can take a block device and start replicating it to another site and it'll be a few seconds behind or whatever you configure, whatever the bound is on your asynchrony that you allow. But the sort of the missing piece is all the stuff that sits above this that actually orchestrates it and automates it. Because at the end of the day, the user wants to be able to say, this is my application, and all the YAML stuff that you're feeding into Kubernetes to like define how it's actually being deployed, and you just want to like click a button that says move it to another cloud and do it while it's online. And so, coordinating the movement of the storage as well as the movement of the application that's consuming that storage is sort of where the trick is. And in principle, it's all possible to do manually, but it's really hard to do. Anybody who's actually tried to do a big data center migration knows this all too well. But we're getting to the point where we have all the tools to actually automate it. And so it's sort of getting to the point where we actually have to build them and make them available.
And for somebody who's interested in getting started with running their own Ceph cluster, what are some of the considerations that they should be planning for in terms of the system capacity and network capacity and the scaling factors that are enabled by running Ceph?
I think it really depends on what your plan is to use it for. So I mean, I run a Ceph cluster in my basement, and the requirements there are very different than what you'd have if you're deploying something in the data center to deploy or to support a real application. I think one of the first things to do is make sure you're buying the right type of storage devices. For like a hobbyist basement cluster, consumer SSDs are probably fine because you're not actually writing that much data. But for most production systems, you have to be really careful to buy, like data center SSDs that have the number of write cycles that you're going to need to support in order to actually have the cluster survive for whatever its intended lifetime is, or at least those devices. That's one thing. I think that it's a similar situation with the network for casual usage for just like, my personal data archive. Gigabit Ethernet's probably fine. I don't really need a lot of performance out of it. But in real systems, usually you need 10 gig or 25 gig or whatever it is. And, although you can cobble together all this random hardware and just like throw it at the cluster and it'll, slurp it up and you can build something that's replicated or version coded or whatever. The overall reliability of the system is sort of a complicated function of the reliability of all the individual components. So if you have like really flaky hard drives or old hard drives that you're just tossing into the system, they're going to fail at a pretty high rate. So you want to make sure that you compensate by having a higher degree of replication or whatever it is. So there's no sort of easy answer, I guess. It depends on what you're going to do with it. But we see users doing the full gamut, right? People are buying, pre-built, pre-validated high-end hardware that's like, all NVMe and very reliable high-performance networks, all the way down to people who are, like taking their Raspberry Pis and plugging in a USB stick and like random the cheapest consumer SSDs they can find via like a SATA adapter or something. And it'll all work. It's just a question of how well. It's kind of fun to see what people will build. You just have to, hope that they're paying attention to what their real requirements are.
And as you're scaling the system up and down, does it support things like service discovery via whether it's DNS SD or console or etcd or anything like that?
Internally, Ceph is written so that there's sort of no manual configuration about like nodes and IP addresses and everything like that. Every daemon has an ephemeral IP address that it comes up and binds to and then registers with the monitor to make it discoverable to the Ceph cluster itself. So the monitors are really the only thing in the system that sort of have fixed quote unquote IP addresses, and everything else is totally dynamic depending on what happens to be running at the time. As far as the monitors go, there are a couple ways to deal with that. One is that you can either give them fixed addresses and just configure that on every node. An easier way to do it is to use DNS, where you can have an A record for every monitor, and then you sort of have one central place where the monitor IPs are registered, and then everybody's configuration file just points to the DNS name. It's also possible to use SRV records and have the monitor IPs get discovered that way, but it's not entirely clear to me what value that actually adds over just like having a DNS name that points to the cluster in that sense. As far as having sort of another level beyond that, where you're using sort of zero conf, where you just sort of magically notice that there's a Ceph cluster on your LAN, we haven't done anything like that. I haven't really seen a strong use case for that, but I think in most cases where Ceph clusters are deployed, it's a big enough thing that you want to have sort of a controlled way that you know which cluster you're talking about and where it is, and are explicitly referencing it instead of having too much magic around like finding it and consuming it.
For file systems, there are any number of different types of workloads that are going to be some mix of read and write, and they could be a high volume of small files or a small volume of larger files or some combination thereof. So, what are some of the capabilities that Ceph has for being able to address these different types of workloads? Are there just different tunable parameters for the expected workload, or does it have some sort of dynamic allocation for being able to adjust to the actual real world use case?
There are a lot of tunable parameters that are available, but our goal is always to not require anybody to actually ever have to touch them. And how far you can sort of get to that ideal will vary depending on how weird the workload is. Generally speaking, Ceph does a pretty good job of dealing with whatever you throw at it, provided the hardware is appropriate. If you have like a high IOPS block workload with like random reads and writes, and you have like slow hard disks, then you're not going to get very good performance. It's not going to work super well. But assuming your hardware is appropriate, then it'll do the best it can, best that it can regardless. With the new storage backend that was recently introduced called BlueStore, we sort of took over management of the individual storage devices. Prior to that, we just layered on top of an existing file system, normally XFS, but with BlueStore, we consume raw block devices directly, and we have our own sort of custom-built file system-like thing that stores objects on those devices. And BlueStore does a number of things that try to make sure that it's storing data as efficiently as possible for the given object that you're storing. An example of that is the way we deal with checksums. So one of the big additions that BlueStore brings over layering things on top of XFS is that every byte that you write into BlueStore has a checksum associated with it that's stored. And so normally, if you're just writing objects, we'll checksum on 4K block granularity. But if there are hints from the client that the write is it's a sequential write and it's going to be read back sequentially, then we'll checksum in large chunks, like 128K or something like that, because it's much more efficient. It results in less metadata that we have to store internally. And then the downside being that if you read a 4K block, you have to read the full 128K chunk and verify the checksum on the large chunk in order just to return the 4K. But if your workload sort of knows that that's not going to happen, then we can avoid that work. And then the various components of Ceph are feeding those hints in. So for example, Rados Gateway, when you're doing object storage, it's pretty much all big puts and big gets. The API supports doing sort of a range get where you read a small piece of an object, but it's a sort of a rarely used part of the API. And so RGW is hinting that all the stuff that it writes is going to be written sequentially and read sequentially. And so the way that it gets stored on the back end is much more efficient in terms of the way that the checksums are calculated and stored. Whereas in the block device case, it's sort of the opposite. We don't know what the IOs are going to look like. They frequently are small and random. And so we always checksum on a small granularity. So that's just one example, I guess. But that BlueStore backend, one of the goals in sort of finally taking over that last mile and controlling the way the data is laid out on the block device is our ability to implement those sorts of heuristics and support. So BlueStore also supports compression, which has a whole bunch of similar trade-offs where depending on how big the chunks are that you compress, it changes the way that how much read amplification you might have if you're reading small bits and pieces. But Ceph allows you to set hints and tuning parameters on pools or on file systems or on block devices or whatever, so that all that stuff eventually trickles down into the back end, and it can know for any particular object that it's storing how it should optimize the way that it's laying out on disk.
And one of the interesting aspects of Ceph as well is that for most platforms that people might be familiar with, where the object storage is distinct from the block storage and distinct from shared file systems, and Ceph provides an abstraction layer on top of a sort of unified storage underlayment, is there any capability for being able to interact with the same data from each of those different sort of abstraction layers on top of it?
The answer is a little bit of both. So in designing the way that we lay out data for the file system, for the S3 object store, and for the block, we sort of optimize for each of those use cases separately. So they're all consuming Rados, but they're using Rados and laying out their data in Rados differently. And the idea there is that because the semantics of those APIs are different, they have different workload patterns and different requirements. And so it didn't make sense to layer our S3 object storage on top of a file directory, for example, because of the way that, mostly around the way that objects are atomically replaced when you do a put, and you might have versioning, and also because of the way that an object enumeration in the S3 API works. You couldn't really check all the boxes and do it optimally, and also do it the same way for two different sets of requirements. So generally speaking, each protocol lays out data differently. That said, we've added support in RGW in the gateway for exporting a bucket as NFS, because what we found in the real world is that what most organizations have today are like a bunch of NFS servers where they're dumping their data, and they're trying to make this organizational transition to object storage, and they can't just do it overnight, and they can't like rewrite everything all at once. And so they need to A, copy all their data over, and B, they frequently have some parts of their infrastructure that are still want to dump all their data out over NFS, even though the new parts of their infrastructure are reading it out of the object store. And so having this sort of dual protocol access for objects is critical to making that transition. And so that's something that we added, I guess, about 2 years ago now. We've talked about the idea of having RGW buckets that are sort of backed by a directory in the file system, also, so you could sort of have that dual protocol access to the file system storage. But we haven't seen a whole lot of user demand for that, because in most cases when you're using object storage, the object is sort of where you're trying to get to, and having sort of suboptimal file access in order to get there is fine. And we don't really see that happening in the other direction. And on block, we haven't had a lot of need for it. Usually when people want to access a block device as a file, it's for backup or just to like import or export. And so there's a whole set of tools around doing that already. And being able to like mount a directory in your on your server that like shows your block devices as files isn't all that important. Although for a while we did have a Fuse tool that did exactly that, but I think it's not supported. It might even have been removed. I can't remember.
And in terms of use cases, there are a huge variety because everybody needs to store data in some fashion, and there are multiple interfaces to that. And so it sounds like a big driver of Ceph within an organization is for being able to provide this multi-cloud capacity, or being able to migrate data across infrastructure. And when I was looking through the documentation, it looks like one of the pieces that's actually supported by that as well is for being able to use it as the underlying storage system for database engines or for sort of more big data workloads as well.
Yeah, we see sort of a number of common use cases fall out. Backing an OpenStack cloud and all your virtualization is one of them. Just general purpose object storage, where you just have your reams of data that you want to dump into a scalable and cost-effective system, is one. One of the emerging sort of use cases that we're seeing a lot of right now is the sort of quote-unquote data lake, where you're storing a bunch of data in RGW in the object store, but then you're running Hadoop on top of it. And that's something that we've invested a lot of work in making that work and perform really well. And we find that a lot of people find Ceph to be a good fit there, because they have sort of a mix of wanting to store a lot of data in a general purpose object store and have all the advantages of having a sort of a rich S3 API that lets you access that, and also needing to run their analytics on top of it. And in sort of the past, you would have to have like a Hadoop cluster that you would copy all your data into HDFS and then run your analytics and then copy the results back or something like that. And this sort of eliminates that step. And interestingly, sort of the one of the motivating concepts of the way that HDFS was built was this idea that you'd break up your map component part of the computation into pieces, and you'd run the compute right where the data is. In reality, with sort of today's network speeds, that's become less of a challenge and less a requirement. There's really not a noticeable benefit from doing that. And so having everything go through, a set of Rados gateways or whatever is fine with sort of today's hardware. When you're not optimizing for these gigabit links and slow hard drives that you were in the past.
And what are some of the situations or use cases where you would advise against using Ceph and direct somebody to use an alternative project instead?
This discussion actually came up recently for me when I was thinking about the NVMe over Fabrics sort of hardware trend and where that was going. And the thing that really came out of that is Ceph is really focused on providing a reliable storage service. So every bit that you store in Ceph is replicated or erasure coded in multiple devices, and it's all set up so you can tolerate multiple points of failure and all that stuff. And there's a cost that's associated with that, right? It costs latency. You have to buy more hardware and so on. And there are a lot of use cases that just don't require that, especially as we move further into the sort of cloud native way of building applications. A lot of worker nodes or whatever are containers are stateless. They need some storage because they're like deploying a little mini operating system and doing a bunch of stuff. But a lot of the data they store is either reproducible or throwaway or temporary or can be rebuilt or whatever. And you really don't need to pipe it into this like highly reliable storage system. That sort of. So I think it's the biggest thing is to separate out your ephemeral storage from your reliable storage and think of those two sets of requirements. It's often easy to just deploy a cloud, your OpenStack cloud, and back everything by Ceph because you just don't have to think about it. But you're sort of throwing away some money when you do that because a lot of times those VMs actually just need ephemeral storage that is fine to lose in the event that the system crashes or whatever happens. And I think that the challenge there is really around building the tooling to make that easy to manage. One of the benefits of having sort of a quote unquote unified storage system like Ceph that gives you file, block, and object is that you can basically take all of the storage devices in your system and feed them into Ceph and manage them all centrally, and it'll deal with balancing data and setting up different pools and different types of storage devices and all that instead of having to sort of manage different sets of hardware for different workloads. And when you have a bunch of storage that's ephemeral and you actually don't want to have replicated at all, that introduces sort of a second class of storage devices, and figuring out how much to allocate to each of those pools becomes a bit of a burden. So one of my goals is to figure out how to sort of tackle that problem from sort of a whole data center perspective of how you allocate your storage to the system in a way that makes sense in a Kubernetes environment. I think that's something that eventually we're going to have to make easier for users.
And as somebody who has been involved in one project for so long, and particularly a project of this breadth, what have you found to be some of the most interesting or unexpected or challenging aspects of that work and of that effort of building Ceph and the community, or new things that you've learned that you didn't expect to have to encounter in the process?
It's been a very educational experience as far as how communities work and open source communities in general. I was definitely naive when I started and we open source Ceph. I thought that the contributions were just going to pile in and everyone was going to make it all better and it was just going to be sunshine and roses all the time. The reality is that building communities, especially developer communities, takes a lot of work and it takes a long time. For one, I think the other thing is that it's tempting to try to make Ceph all things to all people because there's such a breadth of users and a sort of a crazy variety in like the environments that people want to deploy Ceph. And in theory, you can sort of fit it to do all kinds of different things, but you can't because you have to limit the scope or else you'll just be overwhelmed with the complexity of the system. And when it comes down to it, there are certain things you have to choose and what you're optimizing for. And so figuring out what the right balance is in terms of sort of where to focus the project and where to target it and what not to do is always hard. And I think the last thing that I didn't anticipate is that it's actually a lot of work to keep up with what people want to do with the system. There are a lot of instances where you have a contribution from somebody who's like trying to implement some new feature. They want to add, some geo-replication capability to the file system, for example. And oftentimes you'll have a group of developers that go off and do a lot of work and actually build like a fairly complicated set of changes to do it. And it's a lot of work for the core maintainers to like actually find the time to look at it in detail and provide meaningful feedback to figure out how to review it and fit that into where the larger project is going. And to try to get those developers involved with the core development sooner in the process so that they build something that is aligned with where the project is going, and avoid sort of instances where you build something you invest a lot of time to something that's pretty complicated and it just isn't quite right and it ends up not getting merged and being somewhat wasted effort. It's a challenge, right? Because you have a small set of core developers and they have all this other stuff that they're trying to do, and figuring out the balance of how to engage with those people and get them to engage, and also get the things done that are sort of more on your immediate task list. is pretty hard.
And what are some of the plans that you have going forward for the future of Ceph?
World domination. No, I think at a very high level, my goal for Ceph is that the first choice for reliable storage in any data center environment should always be an open source option. One should never feel like the first thing that you reach for is a proprietary system, and one should never feel like you have to reach for the proprietary system because the open source system isn't good enough. It should be quite the opposite, and it should be that the place where the most innovation and the most exciting new development is happening is the open one because that's the one that's most accessible to researchers and experimenters and all the rest of it, right? That provides all the transparency. So that's sort of the high level goal. The more tangible immediate goals for Ceph really center around a few key areas. One focus area is performance. Ceph grew up with hard drives and later SSDs that were like SAS and SATA attached. The new world is like PCI attached flash and even like non-volatile memory technologies that are sitting right on the memory bus. Whole new level of performance that's required, and just the way that the software is written itself needs to change. So there's a big effort underway right now to refactor a lot of the code in the OSD in particular and rewrite it using new software frameworks. So we're looking at C Star, which is a C++ framework that sort of explicitly shards work across cores and tries to never move control across cores. So all the CPU caches work very efficiently, and it's all sort of futures-based run to completion style putting the software together. So that's one big effort, and it'll enable us to use things like DBDK and SBDK, these software toolkits from Intel that allow you to move the drivers for both your NVMe drive and your network card into user space and into this whole sort of co-scheduled runtime environment for very high performance. So that's one effort. Performance is really important because the hardware is changing. The other big area is around usability. Ceph was sort of written by Linux hackers and developers, whatever, and initially targeted like OpenStack cloud users who are very technical. And so it's built up this reputation of being sort of complicated, lots of knobs, hard to deploy, hard to manage, hard to understand. And that's inhibited adoption in a lot of other spaces. And so a lot of effort now is going into making the system more self-managing, which is important both for sort of non-expert users and also for making the system work at scale when you have 10,000 nodes. Like, you really can't have somebody who's like looking at all the details to try to do things manually. You really need to automate all of it. So there's a big focus there. And then the last thing is really around platforms and making stuff work well with the emerging application platforms, specifically Kubernetes is the main one. Ceph should be, if it isn't already, the first choice, an obvious choice for providing storage in a Kubernetes environment. And so we're investing heavily in projects like Rook, which is an operator for Ceph that automates the management, deployment, and makes it very easy for Kubernetes applications environments to consume Ceph storage.
Briefly, the mention of C Star is very interesting because I know that it's been very sort of battle tested in the ScyllaDB project where it was originally created. So it'll be interesting to see how that manifests in terms of its utility within Ceph. That definitely sounds very exciting. And are there any other aspects of the Ceph project or anything related to it that we didn't cover yet that you think we should discuss before we close out the show?
I think we covered it.
So for anybody who wants to follow the work that you're up to or get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I would like to get your perspective on what you view as being the biggest gap in the tooling or technology for data management today.
Let me think about that one. I think it's really around, I think it's this emerging data services space as organizations move to multi-cloud and hybrid cloud environments. There isn't a lot of software and tooling and sort of underlying capabilities that allow you to manage data across these multiple footprints, and certainly no open source tools to do it. And so this is a key area where we're investing, and I think it's going to be increasingly important as people, shift from their more traditional IT styles into this new world of cloud native, multi-cloud, hybrid cloud environments.
All right. Well, thank you very much for taking the time today to join me and discuss the work that you're doing with Ceph. And thank you also for the work that you have done on that project. It's one that I have been keeping an eye on for a while and will most likely be working on deploying in my own environment for shared file storage. So thank you very much for that, and I hope you enjoy the rest of your day.
Yeah, thank you very much for having me.